The last chapter for us to cover is predictive modeling. And predictive modeling can be a lot easier than descriptive modeling because the only goal in predictive modeling is to make, you guessed it, predictions. When you think about the equation, the y hat equals b0 plus b1x, I'm going to put a 1 next to that x. The predictive side of the equation is the y hat, so once again we focus on the predictions and how well the predictions do. The descriptive side of the model would be the other side of the model, which has, and we reviewed last week, the x's are found, first task, the coefficients of the x's are found, and then we interpret or describe in a descriptive model. This is your descriptive side over here, and the other side is the predictive side when it comes to doing analytics. So when we are doing this, we are going to look specifically at how well we make these predictions. How close the model is to the truth is something more we do in descriptive modeling. We still kind of want that, but the predictions are the main objective in predictive modeling. Remember from last week how close a model is to the truth won't really matter here, and this is something like AIC or AICC. That's a measure we use for descriptive modeling. Here in predictive modeling, once again, it's going to be about predictions. It doesn't really matter how we get them, but how close the predictions are and how well we predict is going to matter. AIC focuses more on the descriptive model and how close we are to the actual true coefficients for the model, rather than how are the predictions actually doing. So think about this model right here. If you think about it, we have a linear model, so the line is put through, but when it comes to the data follows a polynomial or parabolic form. So there's the blue data showing you right there, and the linear form has been fit to it. Obviously, describing this as a line doesn't really make sense. But when we think about how well it predicts, it can actually have an r squared kind of close to maybe like 0.98, let's say. Probably about what that r squared is, because about 98% of the variation in that data is explained by the line. You know what? That's pretty good. That means the predictions are going to be kind of close. We're not going to have too many misses, at least looking at it visually. There's no big outliers. There is a huge trend to the data. So is this the true model? No. Actually pretty far away from what the truth is, because a line is not what this data forms. It's going to be something different, but the predictions for this are pretty good. So as a descriptive model, maybe not the best describing it as a line, but as a predictive model, it predicts pretty well for the points. Now the generalization error is going to be super important right here. When you think about generalizing something, it means how does it work on new data? So the idea of new data and generalizing well means if we train our data over here, and then we have new data that the model's never ever seen, how well does our model make predictions on this data? Now the hard part about this is the RMSE that we get is sometimes called an RMSE train. Over here, this would be the RMSE that it generalizes to new data on. What is RMSE? It's a typical miss the model makes, root mean squared error. The error is the miss. We root it and square it to turn it into positive values and take mean to make typical miss. So overall, this is the RMSE on new data. So this would be over here. And this is the RMSE, the typical miss on the original data. So you want it to do well on the data it's created from, but then data it's never seen, new data, you want it to do well on that data, and then it can predict. That's the goal of a predictive model, is make predictions. So there are plenty of real-life examples where things don't generalize, like maybe you study too much for an exam and you overlearn it. We often call this overfitting. The idea of overfitting right here, what if you were to have an exam coming up and you were to study a practice test hundreds of times? You just studied the practice test till you aced the practice test. You're like, I can ace this practice test, get 100 on it, but meanwhile, when you take the actual test, you make a 60 or 70. Well, that's because you overlearned the original data. You took the training data set, which was the practice test, and you memorized it so much that your understanding didn't generalize to the test. We're going to have ways of handling that, and some of the ways will be presented today. Additional ways are presented in 474 when we go deeper into data mining. So the idea of overfitting, once again, it's a huge problem in predictive analytics. Think about this. You have an RMSE, which is typical miss of your model, and you make it on your trained data. And on the training data, you miss the prices of homes. Let's say you're predicting for the Knoxville area by $10,000. That'd be pretty good if you're trying to predict the sale price of a new home by $10,000. Maybe you predict the house is going to sell for $400,000, it sells for like $385,000. That's about $10-ish thousand because you don't always miss by this. This is your typical average miss when you predict. But what if when you try it out on a new data set, and we'll call RMSE, we'll put a G for generalization to new data, you usually miss by 200,000. So in practice, when you use this model outside of the data it was created on, it completely flops. It does no good. And this is the idea of overfitting. What you want when a model's not overfit, these two metrics are going to be very, very similar. So if they were perfectly the same, not that extra zero right there, if they were perfectly the same, the model would work identical to how it does on the original data as it does on new data that it generalizes to. So with this right here, let's take a data set right here, to launch data set, and we have the sums of squared error on the train, which is how much error there was summed together from the training data set. And let's see what goes on right here as we try to reduce the sums of squared error. Remember, that's our goal with modeling, is to have as small as a miss as possible. We're just going to keep adding in more variables here, x1, x2, x3, x4, x5. And here's what happens. Notice how the model does on the original data keeps going down. Every time you add x variables, the model keeps doing better and better and better. Also, you might see metrics like r squared adjusted going up. Excuse me, r squared adjusted could go down because that one compensates for more x's in the model. R squared would go up too. Misses go down. But here's the interesting thing. Over here on the other color, this goes down, then it goes up. This is when overfitting occurs. Overfitting is going to start to occur here. Let's put a different color line. So purplish here. Overfitting, even more overfitting, even more, even more. And this gap between how well your model does on the original data, this gap right here, that gap is the amount we are overfit. There's the amount we are overfit. You see, the overfitting gets worse and worse and worse. So where about would you want? Well, if we're trying to pick a good spot, there's many answers to the questions. Many statisticians might come up with different ideas right here. I would probably go with right about here-ish, where they cross, where it does about the same on the original data as it does on the new data. So that way it does about the same. Like, here's how I think it'll do. And oh, look, it does about that same on new data. Your model does like it should, like we expect it to. So you don't want this idea of overfitting, that your model works on data, and then when you try it out on another data set, it just fails completely. So this is where we get a training and holdout sample. So the training data set right here is what we build our model on. That's what we've been doing all semester. You've been using training data to make your model. So you've been training your data, understanding the coefficients, and then what is a holdout sample? It's sometimes called a test data set, but the holdout sample is data you leave out. So what you can do a lot of times right here is take your data set and take 30% of your data over here and not use it to create your model. It kind of sounds counterintuitive, but you're going to not use a certain portion of your data to then test your model on it. So this would be the trained data, and this would be the holdout data. The holdout data lets you see if your model properly works. That's where we get the generalization RMSE from. How much do we typically miss on new data? So what does this first portion do over here? This one right here, it learns the coefficients, it creates the model. What does this one do? It's going to be used to test to see if our model actually predicts well on new data. Now we have, if you notice, 3 different RMSEs. We've already talked about 2 of them. RMSE of the training is the typical miss the model makes on the data it was created from. How well does it work from what we learned from? RMSE of the test or the holdout, they're the same thing. Some people just call it the test data because we are going to test on it. Some people call it the holdout because you hold out the data. So they're synonymous right there. But that is how does it work on new data. But then we get to this middle one, which is the one where people usually get confused, which is the RMSE k-fold, or sometimes known as the RMSE validation or cross-validation. This one is used as an estimate of how we will do on new data. And so you might say, well, why do we need that? And this is a question I always ask, like, why would we ever do this? Why would we come up with an estimate of how it'll work on new data? Well, the estimate of how it works on new data is how we're going to pick the model. If we pick the model based on how well it does on the holdout, we'll just fit the model to the holdout. That makes sense? That was something that confused me a lot. But if you just pick on this right here, if you say, I'm going to pick my model that works best on new data, well, then you're just fitting to the new data. We are going to pick our model on how we estimate it'll work on new data. So we're going to have to figure out how to do this k-fold cross-validation process here in a moment. But the way we pick the model is how we estimate it'll generalize to new data. This is our best guess or an estimate of the model on new data. And then we see how it works on new data. And we want those two metrics to be about as close as possible. The closer they are, the better. Usually your holdout does worse, higher RMSE. It happens every once in a while it's lower because sometimes it does a little better by random chance. So you want these two metrics to be pretty similar. If the holdout's a little bit better, that's all right. If the holdout's way worse, that's not a good thing. So how do we do the k-fold cross-validation process? Well, the k-fold cross-validation process states that we are splitting our data up into k chunks. Now, when we do this into k chunks, one of the chunks will be used to validate, and the remaining k-1 chunks will be used to create the model. And then this is an iterative process right here, and you'll see a graphic in a moment, where we make the model on the remaining chunks, test it on the one chunk, make the model on the remaining chunks, test it on the other chunks. Here you can see it. Notice how there's holdout data over here on the side as we go through the rounds of the k-fold cross-validation. Now this is k-fold cross-validation 5, where we had 5 splits. The data was split up into 5 chunks, chunk 1, chunk 2, chunk 3, chunk 4, chunk 5. In the first round of it, chunk 5 was the validation. So chunks 1 through 4 make the model, chunk 5 then validates to get an estimate of how the model works on new data. The next round of it, chunks 1, 2, 3, and 5 make the model, chunk 4 validates, and there's still the holdout data, which we'll test on the very end. The holdout data is not tested at each time, it's a final test, but we iteratively go through making the model, finding coefficients, and then figuring out an estimate of how it'll work on new data. So with this, this is where we get the k-fold cross-validation from. So we now have an estimate of how it'll work from this process right here, the 5 rounds. What's very interesting is we get an RMSE, a typical miss, but we actually get 5 of them. Every time you run this, you get an RMSE. So the way what you find is you find the mean of it, and then you can also find the standard deviation to understand the variation in what you expect. It's a very good process to understand like how well do we expect our model to do on average, and then also what is the variation in how well we expect it to do. So it's going to do a leave one out right here, the k-fold cross-validation. It's called a leave one out cross-validation. Remarkably, the average generalization error can be calculated without actually fitting the n different models. So with this right here, it is a procedure we run to figure out what's going on, and we can do repeated, sorry, I misread right there. We can do repeated k-fold cross-validation, which just redoes the process again and gets better estimates. The reason we might not do it in predictive analytics is it takes more time, especially for larger data sets, and it just gets you a little bit better of an estimate. Nothing wrong with repeated k-fold cross-validation. So this is just basically doing the process of k-fold cross-validation, doing it again, getting a better estimate. So this is how we are going to build our models right here. We have 2 possible ways at this time, and there's a lot more. First, we could look at all possible models, every single possible model. What does that mean? It's an exhaustive search. So you'd have to figure out every single model and then look at all of them to figure out which is best. Or we could do the search procedure right here, and we're going to see what lowers the RMSE of the k-fold cross, and then see how it finally looks at the end, but keep lowering it till we don't see a decrease. All possible models generally takes too much time, so the search procedure is going to be better. And once again, your holdout is a check of how your model will do. You're not trying to fit your model to the holdout, as in you're not picking the model that works best on the holdout. You're just doing it as a final test. You don't get to retake the final over and over and over again. You want to see that you pick your model and then it works. The point is not to pick the model that works on the holdout, it's to pick a model and then see that it works. Remember that right there. Don't pick the model that works on the holdout, pick your model, then see if it works on the holdout. And you don't search through for the one that works, because then you'll just be fitting to the holdout. So with this right here, we want about 20 to 40% of the data generally in our holdout. So once again, 30% is fine. Some people even use multiple holdouts, like a 10%, 10%, 10% holdout for 3 different holdouts. and then they can get an estimate of how it would work on new data from 3 different data sets. It really depends on the size of your data to figure out how much you put into your holdout. We're going to use k-fold 5 with 10 repeats, so the process of k-fold 5 validation, or k-fold cross-validation with 5 folds will be done here 10 times. And what do we get? Well, taking a look at this right here, you can see the running of the k-fold cross-validation. And look, as we get into more variables, you generally see the generalization error go down. It goes up a little bit at the end, but generally it decreases. And then we want to figure out exactly where it's the lowest. And this is going to be where we'd pick from the estimated generalization error. But notice how it does get a little more overfit, especially at the end right here with this last point, pointing to a little bit of overfitting. And maybe we'd go to 8 variables or so. We'd look at the output right here. We'd look at the data to see when is the estimated RMSE the lowest for the k-fold cross-validation process. So when we do this right here, we would choose about 8 variables in the model, and it's due to the estimated generalization error. And with this, we have tons and tons of models that we could have picked from. So when you think about this, we don't know that we have the best model. We don't know that we have the best model because take a look. Here is our model that is estimated to do the best. Let's highlight it. Our model that is estimated to do the best is over here. Now, the model that does the best would be from the RMSE holdout, which is going to be down here, which means all these models from here down, did better. Why? Because they have a better RMSE on the holdout. RMSE holdout is typical miss on the holdout. So any model below that line has a better typical miss on new data. So how can we figure out similar models? We use what is called the one standard deviation rule. The one standard deviation rule says when we calculate our estimate of the typical miss, we can also calculate the standard deviation of the typical miss. So with this, any model within one standard deviation is basically similar. So we generally go for the simplest model. Think of Occam's razor, where we were trying to make a parsimonious model where we don't want it to be too complex. If the models have about equal explanatory variable, but one is simple, more parsimonious, then we would pick that model right there. It's not always simpler is better. If it's equal and simpler, we'll pick the simpler model. So models within one standard deviation but are simpler are the models we will pick. So here we are with the build model output. It's running the best GLM, all possible procedure in the background. Let's take a look at the formula. So the first thing you'll put in is your y tilde x, then your data equals. Type is going to be predictive modeling. We have k folds 5 with 10 repeats, and the seed is going to control the randomness. Make sure you know what you're inputting into this, y tilde x, comma data equals. Type equals predictive for predictive modeling, k fold 5 for 5 folds, and repeats for doing the process 10 times, and seed if we want to control the randomness. And so here we go. We are building our train and our holdout first. Notice we are subsetting the data by picking train rows right here, and then we have the train and the holdout data being split off into their own subset. We take the train rows and remove the train rows. Here's the output of the build model procedure. What we get right here is the best model, which is all the way over here, has the lowest estimated generalization error. Look how the star is the lowest on this plot. But anything near the dashed line or below the dashed line is within one standard deviation of it. And the simplest model is going to be right there, and it only has in it 2 variables. So which model would we prefer to use? Well, for predicting body fat, the weight of an individual and their abdomen measurement does pretty much as well as age, weight, neck, abdomen, hip, thigh, forearm, wrist. Imagine you just have to ask someone their age and then measure their abdomen, and you get a pretty good estimate of their body fat. Just about as good as the 8-variable model? Well, I'd say that's much better to use. And here we are. Here are the typical miss, the standard deviation. And the standard deviation is how much we are probably about off by in our estimate. The estimated generalization error is how we estimate that we'll miss on new data. That's from the model we picked. And here's the best model. Look at the differences between these. I mean, they are only off by just 0.11. They're virtually identical, if you ask me. So using the 2-variable model and the 8-variable model, really not much of a difference at all. And you can see that the predictors in the two-variable model, there's a lot less. So it makes a lot more sense to use the two-variable model. We can get the estimates right here after running the build model procedure using bm.out and $best model. So this is where our best model is stored. And we get the estimate of the intercept, the estimate of the weight, and the abdomen's coefficients. So we would have down here the model we could write out using those estimates. And once again, these black bars right here, the bottom black bar is where your best model is. And this one right here is going to be simplest. Simple model right there. So anything underneath that dashed line is going to be virtually identical to your model. We could definitely pick that model right there because it is about virtually the same as the 8-variable model. And that's a different data set right here. We're predicting diabetes. So let's go ahead and see how it works as we split the data up into our training data to build the model from and the holdout data to test it on, and then running the build model procedure on it right here. So if you notice, we have the misclassification right now because we're doing a categorical variable. But we can still get an estimate of the variation within the misclassification rate. So the best model misclassifies about 19.14, and then it could be off by about 1.4%. And the model that is virtually identical to that is a one-variable model. And I would bet you good money that the one variable in the model is probably glucose. Think about the best variable, the best model is probably going to be just one that uses glucose right here. And a 3-variable model could use other things like pregnancy and other variables. There it is right there. Glucose is the one-variable model, BMI, pregnancy, glucose. But so the best model uses 3 variables, but the model that is virtually identical to it uses 1 variable. I mean, glucose, diabetes. Makes sense. Here we are with the coefficients of our model. And this has about the same predictive power we would think as using additional variables. And then we can see how it does on new data to test it out. So definitely check out this model right here, see if it works. And from there, we run into some problems. Some categorical variables may have missing levels or may have way too much information with them. And with that, dealing with missingness, dealing with variables that have too much information goes to cleaning your data. Make sure your data is cleaned and you can fit it. Make sure the levels appear at a high enough rate that you actually have information for those levels. Because sometimes if we have missingness or if there's too many levels or there's only one level, we actually have to remove those out. So cleaning your data comes into play before even analyzing your data. Interactions can be really good for descriptive and predictive modeling, but interactions are going to create way more models to consider, even with a search procedure, but especially with build model procedures with exhaustive. So if you're thinking about using interactions, you might get better models, and it's worth testing out. You might spend a lot more time getting those models. You might not get as much of a return as you'd hope. One last note on overfitting. When it comes to overfitting, it's a matter of degree. If you want to see if your data is overfit, take your RMSE holdout over the RMSE of the validation from the k-fold cross-validation. Now your goal is that this is about equal to 1. What would that mean? They're about equal. If it's 10 on the top and 10 on the bottom, they'd be equal to 1. Now, overfitting is a matter of degree because it's going to be more overfit when this is larger on top because it just works on the holdout, has a higher typical miss on the holdout. So when is it overfit? 5% is bad, 10% is really bad, 15% is, my gosh, bad, 20% is horrible. If you notice right there, it's a matter of degree. I'd say 5% is kind of bad and 10% is bad. 15% is really bad and 20% is horrible. What's 6% then? 6% is kind of baddish? I don't know. We'd prefer it be like 1 or 2% worse, 3%. If you have really good predictive modeling, you might get a value something like this right here. And I'd say that's pretty good because now the RMSE on the holdout is only about 2% more than the RMSE on the validation. But if you run it and get something like this right here, well, now the RMSE on the holdout is 18% more than the RMSE on the validation, so it does 18% worse. And that's pretty bad right there. It doesn't, your predictive model is not doing as well on new data as we would hope it would. And that's pretty darn bad. I don't like that a lot. You do get absolutely crazy things like this, though, because now you could get something like this right here, and this is horrific. This is where you're like, okay, my predictive modeling is horrible. Because now 218% more error, if you think about it as over 1. So there's 218% more error on your holdout. This is a model you immediately trash and say, this is not a good predictive model. Immediately trash that model. You're going to have to start over on that one. You do get weird things like this, though. This is a weird one. When you get this, this means that your model is actually doing a little bit better on the holdout than it did on the original data, or we thought it would do, excuse me, because the validation is being used. So it's doing a little bit better than we thought it would do. So hey, that's great. That's great. I would be concerned if I got something. I'd wonder if the analytics were having problems. If I got something like this right here, if it does that much better, I'm like, how am I doing that much better? Maybe there was an outlier or something weird. So I'd want to look at the data then and be like, why am I doing that much better on the holdout? Or did I flip the numbers? Because I've seen that happen to people too. Make sure you understand what this means right here with overfitting when you look at the ratio of how you do on the new data versus how you were expected to do on the new data. Have a great semester and good luck on the final. Go Vols.